We're going to be talking about friction in today's video lecture, but before we get into friction, I want to go over the normal force and help you understand the normal force a little bit better because the normal force is integral to understanding friction. Now, as you recall, the normal force is the force that keeps things from going into surfaces. If I place a book on a table, the normal force pushes the book up to keep the book from going into the table. So gravity may be pushing the book down. I may be pushing the book down, but the book will not go into the surface of the table because the table pushes back. And the force it pushes back with is what we call the normal force. Now, we call it the normal force because it is normal to the surface. Or, in other words, it is perpendicular to the surface. When I say something like a vector is normal to something, I mean it's perpendicular. So the normal force is perpendicular or normal to the surface. Okay? Now, a book with a mass m is sitting motionless on a table. What is the normal force on the book? Well, we're just going to make a free body diagram. Here's my book on the table. I have the normal force pushing up. I have gravity pushing down. The book is motionless, that means acceleration is equal to 0. If acceleration is 0, that means there is no net force on the book. So the sum of these forces must equal 0. Therefore, the normal force on the book is just negative the force due to gravity, due to the earth on the book. And of course, gravity is just mg in the negative j hat direction, the negative y direction. That means the normal force is just mg in the y direction. Let's change the problem a bit. A book with a mass m is sliding across the table at a velocity of 0.133 meters per second. What is the normal force on the book? Well, our free body diagram, we still have the normal force up and gravity down. There's still no other forces, and because the book is moving at a constant velocity, acceleration is still 0, which means that the sum of the forces is still 0, and once again the normal force is mg in the plus y direction. Okay, let's modify the problem once again. A book with a mass m is sliding across the table. At time t equals 0, it has a velocity of 0.133 meters per second. Friction is slowing the book down with a force of F friction on the book. What is the normal force on the book? Well, let's do our free body diagram. We've got the normal force going up, we've got gravity going down, and we have friction slowing the book down. So, force equals mass times acceleration, right? So the sum of the forces is equal to the acceleration. What is the acceleration? Well, it's something in the x direction, right? So I don't know the value of the acceleration yet, but I know that it's in the direction. It's in the x direction. The book is not moving in y. So that tells me that the sum of the forces in the y direction have to equal 0. And the sum of the forces in the y direction are just the y component of gravity plus the y component of the normal force. Gravity is downward, so the y component of gravity is negative the magnitude of gravity, the magnitude of the force of the earth on the book. And the normal force is upward, so the y component of the normal force is just plus the normal force on the book. And those have to add to 0, so I solve that, and I find then that the normal force is equal to mg, just like it was before. So the fact that we added friction didn't affect the normal force because the friction was perpendicular to the normal force. Okay, let's do something a little more complicated. A book with a mass m is sliding on a ramp which makes an angle theta relative to horizontal. What is the magnitude of the normal force on the book? All right, so now here's our free body diagram. The book is now on a ramp which is at an angle theta relative to horizontal. The normal force is normal to the ramp. It's perpendicular to the surface, but gravity is still straight down. And maybe we have a frictional force. I don't remember. Did the problem mention a frictional force? Well, let's just imagine there is. Okay, so there's a frictional force opposing the object sliding down the ramp. Okay, what is the normal force? Well, F equals ma, right? But now the normal force is not in the x or the y direction, but we know that the acceleration will be something in the down the ramp direction. So let's call that the x direction. Let's redefine our axes. Let's call that the x direction. Let's call the surface normal the y direction. So instead of using a coordinate system like this, let's use a coordinate system where x goes down the ramp and y is normal to the surface of the ramp. Okay, when we do this, now the acceleration is in the x direction, and there is no component of force in the y direction, right? Because there's no acceleration in the y direction. Newton's first law. So in the y direction, we have the y component of the normal force plus the y component of gravity of the Earth acting on the book. And we add those together and we get 0. There's no y component of friction, so we don't include friction. All right, now gravity makes an angle theta relative to the y-axis, whereas the normal force is directly in the y direction. So the y component of the normal force is just the normal force, and the y component of gravity is negative mg cosine theta. So there you go. The normal force is just mg cosine theta. Okay, now let's talk about friction. Friction is a force which is parallel to the surface. So the normal force is perpendicular, friction is parallel, therefore it's at 90 degrees from the normal force. And it turns out that there are two types of friction. Static friction occurs when an object is not moving, and it prevents the motion of the object. So I push on a big box of rocks, and the box doesn't move because of static friction. Then there's kinetic friction that occurs when an object is moving, and its force counters the motion. It tends to slow it down. So I'm pushing on a big box of rocks that is moving, and kinetic friction opposes my pushing and makes it harder for me to keep the rocks moving. Now, which one of these applies to a car tire? Static or kinetic? Well, imagine here's a car tire, and if it's rolling without slipping on the surface, then the part of the tire that's actually in contact with the surface is momentarily at rest with respect to the surface, as you see right there. So there is no slipping, therefore we get static friction. But imagine you slam on the brakes and skid. Now the bottom of the car tire is sliding on the surface, and so that would be kinetic friction. So when your car is not sliding, when it's not skidding, you have static friction at play, even though the car is moving, because the bottom of the wheel is at that instant where it's in contact with the surface, it's not moving relative to the surface. But if you're skidding, then you have kinetic friction. All right, now let's talk more about static friction. Static friction only applies when the object is not moving with respect to the surface. And the static friction force will equal whatever it needs to be to keep the object from moving or from slipping. All right, so the static friction force is whatever it needs to be. But there's a maximum that it can be. The static friction force will be less than or equal to mu sub s times the normal force. And mu sub s is the coefficient of static friction, and that's a property of the materials that are rubbing together. So if you have a car tire on a dry road, you might find a coefficient of static friction for that particular interface. If you have a book sliding down a glass table, there's a coefficient of static friction for that book on that glass. All right? But there's a maximum static friction force, which is this coefficient that has to do with the properties of the material times the normal force. And it kind of makes sense, right? If the normal force, if you push something hard against a surface, then there's going to be more friction, right? Okay, so imagine you're pushing on a book, and what's the force due to static friction? Well, for static friction to apply, that means the book is not moving. So I push on the book, and my forces are, I'm pushing the book, static friction's pushing parallel to the surface in the opposite direction. The force of the earth on the book, gravity, is pointing down, and the normal force on the book is pointing up, right? And we say, oh, well, the force due to static friction is whatever it needs to be to keep the book from moving. In this case, there are only two forces that have a component in the x direction. That's static friction and the force of you pushing on the book. Therefore, the force due to static friction is just going to be equal and opposite to the force you're pushing with, as long as that force is less than mu s times the normal force, because that's the biggest static friction can be. If you push harder than that, static friction will give way and the book will start to move, and now you no longer have static friction, you have kinetic friction. Notice that the static friction doesn't depend on area. That may seem kind of strange, right? That if I have a big book and I slide it on the table, or if I had the book sitting on its spine so there's less area in contact, well, you can imagine if I have less area in contact but the same normal force, all right, then there's less area causing the friction, but the normal force is bigger on the area that you have, so the effects of area cancel out. Now, the model of friction we're using in this class is good to a certain degree of accuracy for certain problems, but it is not a fundamental, right? F equals ma is a fundamental law of physics. This is more an empirical model trying to model what happens when you have friction, and it won't always apply to everything. For example, ice skating, right? We said that the force due to static friction does not depend on the area, but if someone's standing on ice skates, it's easier to get them started moving than it is if they're just standing on the ice with their shoes. And that's because our model of friction does not apply very well to ice skates. It turns out that if you take your weight and concentrate it onto a small area, you make a big enough pressure to actually make the ice melt. And now you're sitting on top of water, and the coefficient of friction is lower. All right? So there are times when this model doesn't apply, but for this class, this is good enough. Also note that these coefficients of friction can depend on the conditions of the surfaces. For example, a car tire may have a certain static coefficient of friction on a road, but when the road's wet, you have a different coefficient of friction. Anyway, let's do a problem. A book with a mass of 1.02 kilograms is sitting on the floor. You are pushing horizontally on the book with a force of 0.232 newtons. The book floor interface has a coefficient of static friction of 0.133. What is the magnitude of the static friction force on the book? Well, here's our free body diagram. You're pushing on the book to the right. Friction is opposing to the left. Earth is pushing down on the book from in the downward direction, and then the normal force is pushing up on the book. Well, the force of static friction on the book is whatever it needs to be to keep the book from moving. All right, so it just needs to counter the force that you're using, right? So the frictional force is parallel to the surface. It's in the x direction. The only force in the x direction is the force of you pushing on the book. So there we go. So that means that the static force of friction is going to be equal and opposite in direction, equal in magnitude and opposite in direction to the force you're pushing with, so it's going to be equal to 0.232 newtons, as long as the book isn't moving, right? But there are limits to static friction. So before we accept that our answer is, it's just 0.232, it's just enough to cancel what you're pushing with, we need to see if static friction is actually up to the job of keeping the book from moving. So the maximum force due to static friction is the coefficient of friction times the normal force, all right? But what is the normal force? The normal force is just mg. And so the force due to static friction has to be less than or equal to the coefficient of static friction, mu sub s, times mg. Well, we plug the numbers in and we find that the maximum force due to static friction in this case is 1.33 newtons. The answer we got was 0.232 newtons. So what that tells us is that the force of static friction that we predicted is smaller than the maximum possible static friction force. Therefore, we got the right answer. So 1.33 is not the answer. 1.33 newtons is not the answer. It was just a check. If we found an answer and it was greater than 1.33 newtons, then we would say, oh, there's no static friction on this object because now the object's moving. The static friction couldn't stop it. Now we have to deal with kinetic friction. All right, but because the answer we got was lower than the maximum force due to static friction, then our answer is good. Here's another example. A book with a mass of 2.14 kilograms is sitting motionless on a horizontal ramp. Then we start to raise one end of the ramp. If the coefficient of static friction for the surface of the book on the surface of the ramp is 0.143, at what angle will the book begin to slide? All right, so here's our free body diagram. All right, the normal force is normal to the surface, gravity straight down, and the force due to static friction is parallel to the surface. We're going to use a coordinate system again where x is going down the surface and y is normal to the surface. Now, the force due to static friction is whatever it needs to be to keep the book from sliding until it no longer can stop the book from sliding. All right, so assuming that it can stop the book from sliding, then the force due to static friction is just going to be negative the x component of gravity, because the only forces that have x components are the force due to static friction and gravity. And the x component of gravity, right, we just draw a triangle. The hypotenuse is mg, and we want the component in the x direction. That's the opposite side, so that will be sine of theta. So the force due to static friction is minus the x component of gravity, which is then minus mg sine theta. So that's the static force due to friction. But if that is bigger, if we predict a static force due to friction which is bigger than the maximum static force due to friction, then the book's going to start to move, right? So that's the static force due to friction, but we know that that has to be less than or equal to the maximum static force due to friction on the book, which is the coefficient of static friction times the normal force. Well, the normal force is just going to cancel the y component of gravity, which is the gravity times cosine of theta. So that means that the maximum static friction force on the book is mu sub s times mg cosine of theta. And so if we set the static force we found up here to equal the maximum it can be, then we can find the theta at which we hit that maximum. So here's the equation. We set those two equal, m and g cancel out, and we find that the tangent of theta has to be less than or equal to the static coefficient of friction, which means the angle at which the book starts to slip is just the arctangent of mu sub s, which in this problem is just the arctangent of 0.143, which is 8.14 degrees. Okay, that was static friction. Now let's talk about kinetic friction. Kinetic friction only applies when the object is moving relative to the surface. And when the object is moving, the kinetic friction you get is just equal to the coefficient of kinetic friction times the normal force. And once again, the coefficient of friction has to do with the properties of the materials. But the coefficient of kinetic friction is not the same as the coefficient of static friction. So if I have two objects, a book sliding on a wood plank, there will be a different coefficient for static friction than there is for kinetic. And generally, the coefficient for static friction is higher than the coefficient for kinetic friction. All right. Now, there's no maximum kinetic friction. There's no change. I mean, you just get this. You want to know what the coefficient of kinetic friction is? It's just mu sub k times n. So imagine you're pushing on a book. Kinetic friction is pushing back. Gravity is pushing down. The normal force is pushing up. The force of kinetic friction on the book is just going to have a magnitude which is equal to the coefficient of kinetic friction times the normal force. It doesn't depend on area, right? Just like the static friction didn't. It doesn't depend on the velocity, unless the velocity is 0, and then we have static friction. But as long as the velocity is non-zero, this is the force that I get. I just get it. And it doesn't depend on the acceleration. I just get this force. So here's a problem. A book with a mass of 1.42 kilograms is sliding down a ramp which makes an angle of 17.2 degrees relative to horizontal. It is initially moving at a velocity of 0.452 meters per second. If the coefficient of kinetic friction for the book ramp interface is 0.223 and the coefficient of static friction is 0.443, how long will it take for the book to come to a stop? Well, the book is moving, therefore this is kinetic friction, not static friction. We don't need the coefficient of static friction. That's just a distractor to see if we really knew how to set up this problem. We're not just plugging things into equations. All right, so let's draw our free body diagram. We've got this object sliding down a ramp, all right? And the ramp makes an angle of theta relative to horizontal. We've got the normal force, we've got gravity, and we've got the force of kinetic friction on the book. Now, F equals ma, right? And what is the direction of acceleration? Well, if we use our coordinate system, once again, where x goes down the ramp and y is perpendicular to the ramp, normal to the ramp, then we know that the acceleration is going to be in the x direction. So the sum of the components of forces in the x direction equals ma. Well, what has an x component? Well, kinetic friction has an x component. The kinetic friction's x component is negative mu k times the normal force. And then gravity has an x component, which is mg sine theta. So that means the mass times acceleration is mg sine theta minus mu k times the normal force. Well, what is the normal force? We could solve this to find acceleration if we knew the normal force. Well, we find the normal force by noting that there's no acceleration in y, therefore the sum of the forces in the y direction must equal 0. So that means the normal force minus the y component of gravity, which is mg cosine theta, must equal 0. So the normal force is just mg cosine theta. So we take these two equations and plug the normal force we found into this equation, and we get this. And we can cancel out the m's, factor out the g's, and we find then that the acceleration is just g times sine of theta minus the coefficient of kinetic friction times cosine of theta. And great, now we've got the acceleration, but that's not what we wanted. What we wanted to know was how long it would take the book to come to a stop. But now that we know it's a constant acceleration, then we just use our constant acceleration formulas, right? And the velocity of something under constant acceleration is just the initial velocity plus acceleration times time. So we want to find the time when the velocity is equal to 0. And so that we can solve that, and the time is just negative v naught over a. We know v naught, we're given v naught, and we found a formula for a, so we plug that in, and there's our answer. We just plug our numbers in now, and we get 0.557 seconds. All right, now static and kinetic friction coefficients for a given surface and object are not the same. So an object can have a different coefficient of kinetic friction on a certain surface than its static coefficient of friction. And generally, the static coefficient is greater than the kinetic coefficient of friction. So that means that the force, right, the force due to kinetic friction is mu k times n, right? And the maximum force due to static friction is mu sub s times n. So that means that the maximum force possible with static friction is usually higher than the force due to kinetic friction. So the force due to kinetic friction is generally smaller than the maximum force you could have for static friction for a given interface, an object on a certain surface. So here's a little plot. Imagine you are pushing on a box on the ground, and I've plotted the force you exert as a function of time here with blue. So imagine you start pushing, and you push harder and harder and harder as time goes by. Your force just linearly increases with time. Well, what's the force due to friction? Well, initially it's static friction, and the static friction increases in the opposite direction to cancel out your force, such that the net force here in green is 0. But then eventually you hit the point where you've hit the maximum possible static friction, and then the object starts to move. But then if the coefficient due to kinetic friction is smaller than the coefficient for static friction, then the force due to kinetic friction is smaller than the maximum force due to static friction, and that force jumps down, which means the net force jumps up, all right? So there's the force as a function of time. The acceleration then is just the net force divided by mass. So it looks like this, which means the velocity, right? If it starts at 0, suddenly there's an acceleration, and there's a little cusp here, right? That the velocity does not, its slope changes suddenly because the acceleration changes suddenly. And that's why when you're pushing on something, right, and there's friction and suddenly it gives, you feel that kind of a jerk sensation. That's because suddenly static friction's gone and you get kinetic friction. And kinetic friction, the force due to kinetic friction is smaller than the maximum force due to static friction. So the static friction increases to oppose you, and then eventually it gives way, and you get this kind of jump. And then, of course, here's position. If I integrate velocity, I can get the position as a function of time. Okay, here's another problem. A particular car has tires which, on a dry road, have a coefficient of static friction of 0.671 and a coefficient of kinetic friction of 0.488. What is the shortest possible stopping distance for the car if it has an initial velocity of 35 miles per hour? Well, since the static coefficient is greater than the kinetic, that's probably the one we want to use if we want to stop as fast as we can. So we're going to do a rolling without slipping stop. Now F equals ma, and then the acceleration, the force, is just the force due to static friction on the car, right? And we want to stop as fast as we can, so we're going to push the brakes just as hard as we can without making the car skid, such that we get the maximum force due to static friction, which is just equal to, if our car is moving in the x direction, the force due to static friction will be in the negative direction, and its magnitude will be the coefficient of static friction times the normal force. Now, that doesn't have to be the force due to static friction. That's the maximum possible one we could get. Maybe we only push on the brakes a little bit, and we won't get as much friction force slowing us down. But this is the maximum we can get. All right. So, of course, the normal force is mg. So mass times acceleration is minus mu SA times mg. And of course, then our acceleration is just minus the static coefficient of friction times g. This is constant acceleration. We can find the distance we travel with the equation for constant acceleration. But first, we need to know the time. We can get the time by using the velocity equation for constant acceleration, right? We just find the time at which velocity goes to 0. We solve that equation, we get the time. We take our x equation, and then the change in x minus x naught, then it's just going to be v naught t plus 1/2 at squared. We just plug in our values for t, we plug in our acceleration for a, and we solve this, and we get the stopping distance as v naught squared over 2 mu sg. We can plug in numbers, but first we need to know the velocity in SI units. So we'll take 35 miles an hour, multiply by a bunch of things to convert the distance to meters and the time to seconds, and we find that 35 miles per hour is 15.6464 meters per second. Then we just plug in all of our numbers, and we find, our stopping distance is 18.6 meters. Now, once again, it could have been much longer if we had not applied the brakes so hard, because what we used was the maximum possible force due to static friction. But what if we skid? If we skid, then we just get the kinetic force due to friction, right? It's the kinetic force due to friction, which is equal to the kinetic friction coefficient times the normal force, which is, of course, negative mu k times mg, right? And when we're skidding, we don't get to control what force we get. That's just the force that we get. Now, this looks just like the equation we had before, so the math is all the same, and we find then that, delta x, it's the same equation, only with the kinetic coefficient of friction rather than the static coefficient. We plug in the numbers, and we find 25.6 meters. Because the kinetic coefficient of friction is smaller than the static one, we have a longer stopping distance. So that's the idea behind anti-lock brakes. You want to hit the brakes as hard as you can so you get that maximum static coefficient of friction, but you don't want to skid, so you don't want to go past that. So the idea with anti-lock brakes is you hit the brakes and the wheels slow down, it puts the brake on, but it notices if you start to skid, and it lets up a little bit so that it just keeps you right at that maximum static friction force without skidding and dropping down to the kinetic friction force. So again, kinetic versus static friction. So the force due to static friction is whatever it needs to be to keep the thing from moving, but there's a maximum. So this equation right here tells us the maximum that the force due to static friction can be. The kinetic friction is just equal to this. So for the kinetic friction and static friction, we have an equation that looks very similar, but for kinetic friction, that's the force you get. For static, that's the maximum force you get. That's the end of our discussion of friction.